So if everything is okay, then I will start.
Yeah, please.
Thank you, Paul, for the introduction. I want to thank the organizers for this meeting. I haven't been on LPHYS since Kyonju, I guess, and it's nice to join you again. So this is work about the filamentation, and we are the simulations group from Lomonosov Moscow State University. And this particular work was, I'd say, inspired and maybe forced by our French colleagues, Andrei Mizirovich, Aurélien Lar, Arnaud Coiron. So I guess almost all in the room are familiar with the filamentation phenomenon, and in particular with multiple filamentation, which has a long history of the studies, starting from about 20 plus years ago, and many attempts to control this multiple filamentation, including manipulations with the beam diameter, as shown. Let me turn on a pointer with the beam diameter and many more. And the most recent results with filamentation in the free air are connected to the lighting control and and many others long pass propagations with the terawatt beams at 800 nanometers. And the particular work that was motivations for many more studies in the recent years was a work by French group super filamentation in air, and there was a terawatt beam focused by 5 meters, which set such conditions for the multiple filamentation so that the filaments formed before the focus, and the multiple filamentation patterns developed well before the focus, but in the focal region where the photon base becomes shrinked, the so-called superfilaments appeared with a higher plasma density, maybe higher intensity, and this work brought quite a high resonance in the community, and there were many attempts to mimic this behavior with lower energies, where only few filaments were interacting in the focal region, like this work, where the 4 filaments, 2 of them are visible, 2 are behind them, fused together. Some works with another focusing regimes, some works with quantifying the intensities in the filament and superfilamentation regime, even works where the superfilamentation phenomenon was debated whether it is or the fusion is not possible in such conditions. So quite many multi-critical experiments, and as well there was quite a number of multi-critical simulations, most of which were carried out with only few filaments. Actually, if we desire a time dependent at a time in our simulations, because there is a 4-dimensional task which is quite hard to simulate, so quite many works with few filaments, including with the filaments fusion, were made in numerical simulations. With the works with hundreds filaments interaction were performed without the time in the simulations, with assuming the fixed pulse duration during the propagation, and the averaging of the plasma response over the time duration. So then there is a question, actually. Can we indeed simulate the superfilmentation in the actual regime of tens and maybe hundreds of millijoules. What are our possibilities for such a simulations, and which pulse parameters can we afford to simulate? We took parameters from the French group, from Andrei Mazirovich, to investigate what are our possibilities here. And so there is a fluence of the beam provided by Relais R, and it is a 5 centimeter in diameter beam, which were focused by 5 meter in the original work. In here we consider a 7 meter focusing. And if we want to put this beam on the grid, we're actually quite in trouble, because if we desire a 5 micron resolution for the spatial coordinates, then one temporal slice is about 8 gigabytes. That's quite a lot. And actually, the next question, how many gigabytes we have? And currently we have on a machine, we can have a machine with almost 400 gigabytes. Actually, it's just behind me if you look at my camera. So this machine, if we take the whole beam, the whole 5 centimeter beam, with a quite good resolution of 5 micron, it's not the best that that's used in filamentation, but maybe it's quite enough for the air. So we can afford no more than 30 slices in time, and it's obviously insufficient. So we can find ways to reduce this amount, harshly. And the core requirement here is to reduce by a factor of at least 8 each of the spatial coordinate number of nodes in the each of the spatial coordinates. So then we can afford the 1,000 points in time, and I'll discuss that it can be enough in a couple of minutes. So how can we do that? What's the justification for the omitting the time? If we take just a regular Kerr medium without any plasma, regular nonlinear Schrödinger equation, very old equation, very well known, and simulate the focusing by 7 meters from the initial beam, which we took at 20 millijoules, not 100, not 200, but only 20. We'll find out that as we go from 0 to about 9/10 of the focus, we will raise the intensity up to 12 terawatts per square centimeters. That's certainly the point where the plasma is negligible, and this gives us a chance, but the beta integral is not small, it's about pi, and the pi is too much to eat, the pi is too much to neglect. But so this way, this path must be simulated with considering the Kerr effect. And when we do this, when we go with only the Kerr effect and diffraction through 6 meters, the beam is shrinked, and then we can leave out the background, leave out the large grid in space, and take 1/8 of the grid to simulate the time. Then there, let's look at the beam which we have by this moment in Kerr and diffraction simulations, we already can see that self-focusing alters the input beam by this distance. But we have quite a good, we are quite assured that the neglection of the plasma and all the time effects is not so harsh at this point. So maybe we can just take these 2D plus Z simulations and seed them with a temporal envelope. From there on, from the 17 centimeters before the focus, we take the envelope equation, and with a resolution in time of 1 femtosecond and 1,000 points, that's quite not so impressive by this time, 1,000 temporal points. That's quite a way it was simulated in the beginning of filamentation simulations, but okay, that's what we get. From there on, we can simulate the time-dependent problem. And if we run it and we wait, and we have the solution which with the intensity and plasma density behaving like this. So we can see that the intensity raises up to 60, 80 terawatts per square centimeter. We see quite a regular structure that indicates that the filaments interact between each other. We see that the plasma grows eventually close to focus from the regular 1 electron per 1,000 atoms, molecules actually, to the 5 as much if we think that 1 per 1,000 is the filament level, and twice as much if we think that this level of this irregular level is actually a filament level as well. So actually we can see the increase in the plasma density near the focus, and let's take a look at how does this behave in some details. So there will be quite numerous slides when we'll have a look at the fluence of the beam, at the temporal shape of the field at the maximum point, at one point, which is a maximal, where the maximal intensity is attained, and at the spectrum of the radiation at this particular point as well. So we start with going 50 centimeters before focus, and actually some filaments are formed. Some of them start to interact with some of them have quite enough of a plasma, so about 1 electron per 1,000 molecules, quite regular values. Then the multiple filamentation things happen. This significantly before the focus, the interactions, the conical rings surrounding the single filaments, all this quite familiar multiple filamentation stuff happens. At some point, these new filaments born and dying all over the path start to collect into a single strong plasma cord, which is somewhere here. It's in the current slice. It's even quite far from the center of the beam occasionally, and as we can see in time, the maximum of intensity is attained quite on the trailing edge of the initial pulse. So it's delayed regarding the moving reference frame, because if we look for a single filament, the maximum of intensity goes before the pulse center in moving reference frame. But here our maximum of intensity is attained after the pulse center in time, and that's the evidence that these superfilaments, these strong plasma strings, are caused by the secondary filaments, secondary sources, and actually what is fused is not the initial filaments, but their child filaments, if we take the terminology from the classical works. So at some point quite close to focus, all the radiations collects towards the center, and the several strong of different strongness filaments appear, and once again it's quite hard at each point to predict where will fall the maximum in intensity and in time, but they propagate, and after the focus the filaments diverge with several strings, several filamentary structures propagating over the beam. And if we'd like to analyze these dynamics and to analyze how the fusion goes in details, we would consider the differences between the usual multiple filamentation patterns and behavior, and the case of the focused beam. So when the filaments start to be filaments, yeah, the trailing edge of the pulse is distracted by plasma. It's completely destroyed actually, and what goes in the center is a self-compressed, maybe down to 5 seconds, very short pulse, while the tail of the pulse goes off the plasma, goes off the track. It propagates in the form of conical emission, and when there are several filaments, their conical emissions intersect, and in this work, the interference of the conical emissions from different sources, from different filaments, was observed quite nicely, and this is the core phenomenon that leads to the child filament formation in the multiple filamentation. But unlike the collimated filamentation, when we work with a focused beam, we have quite a good chances. So there would be multiple collisions of these rings surrounding the filament. And we have a good chance that they will combine from several sources, and they will form some quite strong bullet, something that is called as a superfilament, maybe. And this thing is delayed in time. It's on the trailing edge of the initial pulses, and then it starts to propagate, and in the vicinity of the focus, it provides us with quite a strong plasma channel that is observed as a fused filament, maybe. To conclude my talk, I like to repeat that we have performed the simulations of 20 millijoule pulse propagation and filamentation in the focused geometry. Maybe that's not a certain limit for the time-resolved simulations, but it's quite close to our current capabilities, and that the pattern of superfilamentation, of this regime of multiple filamentation combined with focusing is quite in good agreement with what is called the child filament formation in the case of regular multiple filamentation. So thank you for your attention.
Okay, so are there any questions to any of you?
This is Martin Richardson here.
Hello.
First of all, can you hear me?
Yes, I can hear you.
Very good. And thank you, Pavel, and good to see you, Olga. And a comment also for the speaker too. Very nice talk. And it's an area that we have in part investigated experimentally. So there's a couple of comments we can make. I'm not sure that we call the filaments in this case children and parents, but maybe it's a good analogy. The way we define it at the moment is primarily in an experimental sense of whether we use a low or a large numerical aperture for the beam, creating the initial conditions for Kerr-Lenz mode locking, for Kerr-Lenz self-focusing, sorry. And in that respect, in our publications, we've started to refer to, quote, the nonlinear regime, the regime that we all are used to, where basically the self-focusing is generated first by the Kerr-Lenz process, and then it's clamped. And it's clamped by some process. For 800 nanometers, it's clamped by the generation of electrons. And then the regime at larger NAs, we have found is not clamped. And basically this regime is very similar to the one that you all been talking about this morning. Here, yes, the ensemble of filaments does not have a chance to basically to clamp in intensity. So you see the increased rise in intensity. And you also predict the increased rise in electron density. We very much agree with that sort of concept. And experimentally, we have found that in fact there is a lot of agreement. Experimentally, we have measured the electron density in the filament in this regime. So in essence, what a regime that we call the linear regime, a regime where there is no clamping, that the intensity rises above the critical intensity significantly, as you point out. And we also see that the electron density in the filament at the time of its birth and immediately afterwards is much higher than the clamped electron density that we observe in the so-called nonlinear filament regime. I must admit that for most of our studies, in terms of applications, we are more interested in the nonlinear propagation regime for a reason that I think y'all will understand, in that in this regime, we can propagate stable filaments for much longer distances over much larger ranges. So hence we have put more emphasis into examining that regime, as I'll point out in a talk slightly later. But nonetheless, your calculations are extremely very interesting, and they're supported by the measurements that we've been making.
Thank you for your comments. I guess that's not such a tight focusing. The 7 meters is still not enough to put the linear regime. So actually, these values are kind of clamped. That's Okay, but I understand what you're talking about. But in this case, the clamping actually happens, and this is a non-linear focusing that is dominant, at least for these initial filaments. And we know, and Olga knows that the long path propagation is of many interests, but that's the case for several other our works. This is about the superfilamentation. But again, I'm quite sure that this is a non-linear focus and not the linear one. And yes, in the tighter focusing, there will not be such clamping as here. We agree.
Martin, thanks for the comment about the experiment. So it's the question of terminology. Is it clamped or not? But it's like this, whatever you call clamped, right? So
yes, indeed. And so when we say clamped, we are looking for clamped intensity and electron density. And we do see a difference between the two. And indeed, this does, I do take the comment with regard to the numerical aperture. I should add that we have done sort of separate experiments where we've deliberately created two parallel filaments and non-filaments, and looked at how energy can be transferred from one to the other, depending upon the regime that they're in, clamped filaments and unclamped filaments. We do see this energy transfer. In fact, energy transfer between clamped filaments and between clamped filaments. And I think there is some evidence we also have a little more difficult to obtain, but some evidence for transfer of energy to unclamped filaments as well. So yeah, I don't disagree at all with the interpretation you're putting on your calculations. And yeah, it's an interesting region. And if we want to call these superfilaments, they're transient superfilaments, that for sure. Yes, so be it. Let's do it.
Well, perhaps we should continue. We're already quite behind, so let's welcome our next speaker, Ryan.
Hi there. Can you hear me?
Yeah, I can.
Great.
Yeah, I can see your screen as well.
Perfect. Well, thank you. I'd like to thank the chair for inviting my talk and interest in our research group at the University of Arizona. My name is Ryan Rhodes. I work under Dr. Jason Jones, and I'm here today to discuss our recent work on molecular dual cone spectroscopy of laser-produced plasmas. And let me just minimize one of these Zoom windows, and we can get rolling. So I'd like to first start this talk with the initial motivation as to why one would want to study a laser-produced plasma. And that is because these are small-scale environments that still contain highly excited atomic and molecular species that can be useful surrogates for studying larger phenomena that can't necessarily be reproduced in a optics lab or easily produced in something, or reproduced rather. Those can include kilonova ejection, which has use in astronomic spectroscopy, detection of added threats and fireballs and explosives, things that very hard and very expensive to reproduce experimentally. The spectroscopy of lanthanide and actinide elements, with a particular interest of uranium detection and its associated oxides, as well as general isotopic analysis. Now, a laser-produced plasma, which is, I guess, if you're not familiar, is just a plasma that's produced from the ablation of some solid by a pulse laser, is used in a technique called laser-induced breakdown spectroscopy to study these atomic and molecular spectra in emission. However, broadband absorption spectroscopy isn't necessarily commonly conducted using this technique, which is unfortunate because you can extract a lot more of direct information from absorption features, not necessarily emission. Additionally, a laser-produced plasma is a transient and dynamic phenomenon. Over the first tens or hundreds of microseconds from the plasma formation, the temperature of this plasma can change fairly quickly. And as the temperature of this plasma changes, the initially excited ionic species it contains start to cool, start to form ground state atomic species in detection. And as those further cool, they start to react within the plasma and form molecular bonds and clusters. So being able to determine the dynamics of the temperature, the number densities, and the interplasmic chemistry is of high importance for understanding these types of systems. Now, a novel characterization technique our group has been applying in the study of LPPs is the application of a technique called dual comb spectroscopy. Our group had previously used dual comb spectroscopy methods to study atomic species and absorption, where we are able to measure atomic lines in absorption with high resolution, with spectral resolution, or with temporal resolution over these timescales that have multicolor and multi-species capability. We are able to use these measurements to determine oscillator strength, atomic column density, or atomic number densities, and excitation temperatures for a wide variety of species. So we're pretty confident in our ability to apply dual comb spectroscopy to the study of plasmas, but this hasn't necessarily been applied previously to our work in molecular formation. Now, dual comb spectroscopy as a technique in broad strokes is underpinned by a specific type of laser source called a frequency comb. Now, frequency comb is a type of mode-locked laser that has specific conditions imposed on its phase or on its frequency stability, where through phase stabilization techniques, the frequency picture of a frequency comb is comprised of individually localized teeth or within your bandwidth, comprised of you can consider them as an array of CW lasers over a broad bandwidth that are individually spaced by a frequency associated to the output rep rate of your laser. So if you have a frequency comb and you are stabilizing either your comb teeth or a parameter called the carrier envelope offset frequency, which is their frequency offset from DC, you have a fixed relationship between one comb tooth and any nth comb tooth by simply these two fixed parameters. Now, this is essential because in dual comb spectroscopy, we need to optically interfere two frequency combs together. And this is achieved through slightly detuning the repetition rate differences of two frequency combs. When the two combs optically interfere and are detected on a standard RF detector, it produces what can be considered a multi-heterodyne measurement, where the beating between the two frequency comb teeth with slight rep rate detuning beat with each other and produces a RF frequency comb. Now, this RF frequency comb, without any loss of generality, contains all of the optical information of the optical comb, except now it's, rather than being in the terahertz domain, it's in the more conventional RF megahertz domain, which is quite useful because through a standard low-pass filter and Fourier transform, we can extract the power spectrum of the light. And for use in absorption measurements, if one measures a reference in a signal dual comb interferogram, we can extract out a absorbance measurement from these two spectra. And as we can see here, we can achieve pretty good results in atomic. This is a resolved rubidium D2 line, and we're endeavoring to achieve similar performance with molecular studies. Now, hopefully I've motivated why we would want to conduct laser ablation. We have achieved dual comb we're applying dual cone spectroscopy to these results in atomic species, and now we want to do that in molecular formation. So we settled on a molecule of interest that we can produce, cerium oxide, which has an electronic transition in the 780 nanometer region, which we can access through frequency conversion of an erbium-doped fiber laser. So to outline our experiments with dual cone spectroscopy, I'm going to walk through the experimental setup here using our two erbium-doped fiber lasers in order to produce the mutual coherence needed between the two frequency combs. We phase lock them to two narrow line width CW lasers operating at 1560 and 1540 nanometers. Our frequency combs operate at a nominal repetition rate of 82.6 megahertz and a repetition rate difference for most of these initial results here at 290 hertz. We convert our light from our 1560 region to 780 through the use of a periodically pulled lithium niobate crystal, and we spatially overlap our two frequency combs on optical fiber and through a polarization combiner. And through optical fiber, we're able to deliver our frequency comb probe beam to our ablation chamber where we're ablating a pure cerium metal target. Now, the cerium target has some degree of surface oxidation on it, which is more of a feature than a bug, as I'll illustrate in a couple more slides, where we're ablating it with an ND-YAG laser operating at 532 nanometers with a repetition or with a duty cycle of 10 hertz and a pulse energy of about 80 millijoules. So we're able to generate the cerium plasma in a vacuum cell with a 50 torr static pressure, or with a 50 torr total pressure under a nitrogen flow, with a probe height of about 5 millimeters with respect to the target surface, perpendicular to the direction of the ND-YAG pulse discharge. Now, in order to achieve temporally resolved measurements from this experiment, we need to have some way that we're able to synchronize our ablation discharge with our dual comb interferograms. This is achieved through an FPGA delay, where we detect our repetition rate difference and use that to synchronize our YAG discharge to a pair of dual comb interferograms, such that we're able to collect a reference interferogram right before the ablation discharge and a signal interferogram with a tunable delay with respect to the ablation discharge. This allows us to have that control of our dual comb interferogram and our experimental data reproducibly with a fixed time delay. So as we change time delay, that can allow us to achieve our temporally resolved measurements. I also want to mention that for initial experiments that we conducted using this technique, we were limited in our instrument line shape resolution by how close to the ablation event we can have our dual comb interferogram and apply because we could only apply an apodization window at twice the time delay from that interferogram. So in other words, the closer our interferogram was to our ablation event in time, the more limited our resolution was. However, in later results, we're now able to apply more robust post-processing techniques that allows us to overcome this limitation and not necessarily be limited in our instrument line shape at these early time delays. But for some of these initial results, we did have this limitation at earlier times. So an initial result that we had from our cerium oxide study was simply looking at our oxide formation as a function of time. What we were able to see corresponded well to known cerium oxide row vibrational transitions. It was the 0-0 band with detectable R, P, and Q branches over a fairly large bandwidth. And we could see that the oxide at the early times would grow, and then go away, which would indicate the oxide forming and then turning into higher order oxides at later times. If we were to zoom in on one of these time delays where we had our highest spectral resolution, what we can see is that we're able to resolve a rich field of rho vibrational transitions in this band. Over a full bandwidth of 5 terahertz, we can achieve a spectral resolution of 1.2 gigahertz. And when comparing these experimental results with known literature values, we see a very strong correspondence with our line detection and the literature values associated with this band. So that gives us a high degree of confidence in our spectral resolution and the ability to have reproducible spectra that is quite accurate over a pretty sizable bandwidth. However, so one of the downsides to the cerium oxide spectra that we're looking at here is that it was fairly hard to directly model. So we weren't able to get as much direct information from the cerium oxide bands themselves as we were hoping for. However, what we did notice is that as we repeatedly would ablate the surface of that cerium target and etch away more and more of that surface oxide layer, we believe it was then reducing the total concentration of oxygen present in the plasma, which then allowed cerium oxide or cerium atomic species to then become present within our detection bandwidth simultaneous to the cerium oxide formation. Now this is this proved to be very useful in so much that our lab had a pretty good experience with analyzing atomic results in these types of measurements. So this could give us a way to detect our plasma, cerium excitation temperature alongside our column density to compare with our rate of molecular formation. So let's just consider the single time delay at 101 microseconds here. What we can do is identify those cerium atomic lines present in our DCS bandwidth. We can apply a Voigt fit to calculate their peak areas for transitions with known oscillator strength. So some of these features that we do detect do not have literature values that we could find, so we could not include them in this Boltzmann plot analysis. But for the ones that we were able to detect, we can simply plot their areas as a function of their lower energy level. And simply through applying a linear fit, we can determine from the slope the excitation temperature for that time delay and the total column density for cerium atomic species at every time delay. So that can give us something that we can then compare with just our absorbance of a band head, so that we can see what the dynamics are between the atomic and the molecular species simultaneously from one measurement of one time delay. And so for every time delay that we can measure, we could see the rate of change in the excitation temperature and the plasma, the atomic column density, and then the molecular absorbance associated with the column density of the oxide formation. Now, as I said, this was the first oxide that we applied this technique to. So we wanted to see what else we could do with this technique to study these types of systems. So the first idea was to take our same experiment, put a different metal target in there, and make sure that we can apply this technique to other species. This was achieved with a different metal oxide, strontium oxide. And then moving forward, we wanted to see if we could take this same method and apply it to a different system or a different molecule of interest. And I will present results from very recently involving titanium oxide spectroscopy, and if time permits, some ideas on aluminum oxide spectroscopy that we would want to conduct. So for our strontium oxide experiment, we use the same laser and dual cone system as I outlined previously with the cerium. And this was of interest to us because of the strong isotopic shift that strontium oxide has compared to similar species. And what we were able to measure at a pretty decent spectral resolution was at the 780 nanometer region was 3 measurable rho vibrational bands with R and P branches identified with our system. However, we weren't able to get as strong of a detection of the band head due to higher order perturbations within this transition. So that was a little bit unfortunate, but it still outlines how well of a measurement we can make with our DCS system for resolving these individual lines and features. But we wanted to keep working with this for something that we can sink our teeth a little bit more strongly into. And from there, we settled on looking at a different metal oxide, a titanium oxide. This oxide has a rho vibrational band in the 500 nanometer region. So while we couldn't use our erbium DOT5 laser system to measure this, we were able to access this using second harmonic generation of a ytterbium fiber dual-com system. Here, through, again, second harmonic generation using a BBO, we can double our light at 1064 nanometers with broadband to an area near 520 to 525 nanometers. This dual-com system has a repetition rate of about 77.8 megahertz and a repetition rate difference for these results at about 456.3. And another useful aspect of looking at titanium oxide here is that this allows us to exploit a database of transitions from the ExoMol project. And through the direct modeling and fitting of the ExoMol database line list through a simulation software called pGopher, we can do a spectral simulation of titanium oxide to compare with our experimental data, which can allow us to extract out the rotational temperature and the molecular column density directly from our fit, as well as producing a residual that can essentially remove our molecular information that's convolved with overlaying atomic lines so that we can conduct further Boltzmann plot analysis like I outlined in previous slides. So these are some initial results that we're having from our titanium ablation experiments. These were collected pretty recently in the last month, where we are ablating a titanium metal target with an Nd:YAG operating here at 1064 nanometers with a higher pulse energy here at 420 millijoules, but under 200 torr total pressure with 55 torr O2 partial pressure. These time delays, ranging from 30 to about 100 microseconds, have a 0.91 gigahertz spectral resolution over a 4 terahertz bandwidth. And here we are not limited by our distance from our ablation event. So all of these are maintained at this low or this high spectral resolution. And here, as I mentioned, we are able to apply our fitting routine with our experimental data to generate a model that can give us our temperature and our column density associated with just the oxide structure. So in this simulation, we were able to fit using a temperature of about 3,800 Kelvin and indicating a column density for this oxide of about 1.2 times 10 to the 15 molecules per centimeter squared. So we're also able to not just use the oxide model, but also the residual to extract out these strong atomic lines that we can then use for our use in our Boltzmann plot analysis to compare directly from the same measurement our rotational temperature associated with our titanium oxide and our excitation temperature from our titanium atomic lines. These are preliminary results, so we still have some more analysis and going through plasma chemistry references to get some higher level analysis out from these results. But some initial takeaways that we have are that the rotational temperature for the titanium oxide is increasing over these moderately long time delays, while the titanium atomic excitation temperature tends to stay fairly high but fairly constant. As far as the column density measurements indicate, both the titanium and the titanium oxide species increase at initial times, but then they seem to simultaneously go down at later times, which might indicate that these are both undergoing chemical reactions within the plasma as the temperature cools and the conditions for the formation of higher order oxides becomes more energetically favorable. So being able to get these types of measurements simultaneously at these time delays is a very, very good it shows good promise for applying this technique in the future for even more applications. Now, a future goal that we have would be to extend this out using the supercontinuum generation and not necessarily limiting ourselves to the smaller bandwidth of second harmonic generation. So rather than doubling our fundamental, we can frequency double our supercontinuum to give us a broadly tunable, versatile dual comb source for studying any oxide or a species of interest. One in particular would be to access a transition of aluminum oxide that occurs at a slightly shorter wavelength than what we're able to access with the terbium system. And this would be quite useful in that aluminum oxide is of interest because aluminum is an additive in explosions. So being able to detect this would be of interest for several communities. While also allowing us to exploit this XML database for modeling and analysis. So to summarize, I hope I have demonstrated that we have the ability to study molecular formation in laser-produced plasmas using the technique of dual cone spectroscopy. That can allow us to acquire high-resolution spectra over a broad spectral bandwidth. And moving forward, we'd hope to expand our spectral access of dual cone spectroscopy for these types of experiments using supercontinuum generation techniques, and further our molecular modeling to account for vibrational temperatures determinations from our oxides, not necessarily just our rotational temperature measurements. And for that, I'd like to thank you for your attention, and I'd like to thank all my colleagues at the University of Arizona and all our collaborators as well that has helped me out with these experiments through the last couple of years.
Well, thank you, Ryan. Are there any questions? Okay.
Thank you for the very nice talk, Ryan. Can I ask you, how exactly do you scan over such a wide range using your dual cone spectroscopy, dual cone thing? How do you scan the frequency?
So because of the broadband structure of the frequency comb, we don't need to scan. We have a pulse laser. So that means we have a broad bandwidth that we're actually filtering down in order to get our measurable band within our aliasing conditions. So because this is an interferometric technique, these the frequency axis is reconstructed through a Fourier transform, but we have all of our colors simultaneously. We don't need to scan.
Okay. So then why do you need not a supercontinuum but a dual cone? What is the advantage of it as compared with just supercontinuum?
So the crux of it is that we're able to get the high resolution of the measurement through that interferometric technique, where we don't need to have, say, for like a Fourier transform spectrometer, a mechanical delay arm that gives you that interferometric signal. So we're able to get that interferometric signal directly from the scanning of one frequency cone pulse with the other. So all of this is happening through our phase stabilization and the mutual coherence between the pulses of the two frequency combs. But all of this is happening just from the, if you consider just the reference frame of one frequency comb, as the pulse scans over the other one due to the slight difference in the repetition rate of the two lasers, we can build up the dual comb interferogram that is that RF down converted frequency comb.
So this is as if delay between the two combs, right? Kind of a delay between the two between the two pulses in a comb, right?
Exactly.
The delay is variable, right? Okay,
yeah.
That's what I was trying to find out. Okay, thanks.
Yeah, and that's underpinned by the difference in the repetition rates of those two.
Yes. The difference in the repetition rate gives the delay between the two pulses in the between two different items in each comb, right?
Exactly.
Okay, thanks.
So no scanning necessary. It's all taken care of.
That's understandable.
So how do you pick the pressure? I noticed that the pressure is reduced, right, relative to the ambient.
Yes. Well, it depends on the oxide. So, for example, in this titanium case, we had a higher pressure than, say, our cerium results, and that's really dependent on how the formation of this oxide favors more or less oxygen. Higher concentration a higher pressure will change the shape of the plasma and the plume dynamics. So a lot of it is just kind of honing in on the right parameter space for each individual's species of interest. So it really changes, honestly, between one oxide to another.
Okay. Well, I guess we should move on. Thank you, Ryan, for the interesting presentation. Next speaker is Professor Richardson. He's the director of the Towns Institute at the University of Central Florida.
I didn't mute it yet.
Yeah. Dr. Richardson?
Yes, can you hear me?
We can hear you. Nice surrounding.
Thank you. Can I share screen, Pavel?
Yes, please do.
In which case, here we go. Do you see that nice picture in the screen share?
Yes, I see it.
And so I will just now full screen this. And just 1 minute. Put myself on a clock watch so that I don't overgo time. So first of all, I want to thank you and Stanislav for inviting me to this meeting, and I hope we can add some small comments to discussion about filamentation that you've already started in this particular session. So I wish to applaud you both for pulling this meeting together. And all the difficulties associated with making it virtual. So what you see in front of us is actually a picture taken at night of filamentation from one of our facilities on our laser range at Cape Canaveral. Not all the facilities you see there are actually part of our facilities. The microwave satellite communication systems in the background are not yet associated with anything that we do. The work that I'll briefly be describing is actually done by a team of scientists and graduate students that work on filamentation and filamentation associated effects. Today I'll really be talking about hopefully just some of those issues. Briefly, some properties of filamentation, which probably I can probably summarize, particularly very quickly, taking into account the audience that is here today. I'll mention some of our work on, more recent work on spatial and temporal structuring with filaments. We've been working on structuring of filaments for quite some time, particularly on the impact of it on the actual laser engineering for those laser systems to create spatial structures in particular. And briefly mention some work on filament. We'll mention our experiments on filament propagation in the laboratory, on one of our systems in the laboratory, and then also similar experiments more recently carried out on the laser range over longer distances through conventional atmosphere, through basically a turbulent atmosphere. And on our laser range, we have the advantage, disadvantage, if you like, of seeing a very large change in the turbulent properties of the atmosphere, diurnal changes from a day to night, and hence the reason why we perform experiments both in the day and the nighttime. And then lastly, I'll mention some experiments that we have done to emulate the propagation of these filaments at much higher altitudes than ground-based experiments. So first off, let me just very briefly go through some of the properties that we utilize in filamentation. I wasn't quite sure of who all the audience would be here, so some of this will be not news to some of the folks in the sorry, some of the folks. How do I get back here quickly? In the, oopsie, I'm getting lost here. I was trying to get rid of a subscreen here. But, yeah, there we go. Okay, so yes, let me be very quickly summarized. Here are some of the features that our experiments on filamentation largely are the basis of. Yes, we, per our previous discussion in today's meeting, we are most of our studies are formulated towards in experiments that we consider or call the nonlinear propagation regime, where the filament intensity and the filament characteristics are clamped for single filaments. Of course, we work with laser systems that can produce many filaments at a time, or as I'll show in a moment, filaments that can be stitched in time. And we have characterized in some detail the formation of the filament itself. You see here a very nice picture of a single filament comprising the core and surrounded by a reservoir, this reservoir being nicely defined by the Townsend profile that is concurrent with the self-focusing regime that we're working in. Well, this next slide, I think I can quickly dispense with, since I think everybody around the table here knows the basic formation of filaments, at least by 800 nanometer light. As we go to longer wavelengths, of course, some of the processes can change in impact, and in fact, perhaps other processes also occur. But I'll leave that for a later discussion. And this next view graph, I probably can also be pretty short of. We defined basically three of these regimes between linear and nonlinear. Basically, the linear regime is one which we discussed earlier by our friends from Moscow State University, where in essence, this is a regime where the electron density is not clamped. Usually the filament lengths are relatively short. It does lead to higher laser intensities. And indeed, some other effects start to occur. The supercontinuum emission is different. The pulse actual shape, the individual pulse shape changes through the propagation regime, and is much akin to some of the the model calculations that were shown earlier this morning. Some of this has already been documented in some of our work and other people's work as well. Just some comments with regard to filament characteristics in general. On the left-hand side, you see some characteristics of the supercontinuum generation. We've done quite a lot of work on supercontinuum generation from filaments, as have other groups. I won't really discuss much of that in any detail today. Yes, if one can produce a single filament, then it looks like the characteristics I was shown here on the extreme top right. But in most cases, with laser systems that can produce energies much greater than is needed for a single filament, hundreds of times more energy, then indeed we are in the region of the multiple filaments. Yeah, so the beam as it exits the laser is pretty much shown here. The characteristically shown here consists of multiple filaments or multiple intensity peaks that lead to filamentation. If you project that farther down the range and then look more precisely at the filaments themselves, you can see the individual filaments, and around each one of these individual filaments you see a sort of penumbral emission. The wings of the Townsend distribution, if you like, are forming. And well, why do we show this? Well, firstly, we show this from the viewpoint of, well, how the light is, in fact, how each filament needs to be supported by this penumbral emission. No penumbral emission, no filament. The filament, and if you independently interfere with this penumbral emission, then you will kill the filament. Well, killing the filament, indeed, you can kill the filament various different ways. On the left-hand side here is shown an experiment we did some time ago, actually still not yet published, whereby we deliberately presented in the center of the filament, we presented basically a very small absorbing obscuration, and we moved that obscuration through the film, through the focus regime, through the focal regime. And you can see two things. So the obscuration itself was of the order of 150 microns or so in diameter, so smaller, about the same width as the half width of the Townsend profile, characteristic Townsend profile half width, and as a consequence, much of the light surrounding that obscuration was directly transmitted past it, and as a consequence, there was sufficient energy in that light, the light that passed by the obscuration, for a filament basically to reform downstream. And you see how this filament reformed downstream. Bit of a complicated photograph there, but really this summarizes the reformation of this filament depending upon where the obscuration was placed in the on-axis. Suffice it to say, we have this sort of control over the formation of filaments by manipulating the use of the penumbral field around the filament. There's another way of looking at this, was in a series of experiments that was led by Daniela Reyes, one of the senior scientists working on our project. Well, these were the experiments where we deliberately looked at the interaction of individual filaments. In essence, we created two parallel beams with energies above or below the energy required for a single filament, and we varied that intensity to create single filaments or powers below single filaments. And separately, we arranged for these filaments to be moved closer and closer together. And you can see very clearly from these bottom set of diagrams here, you can see how when the two penumbral field distributions of the individual filaments start to interfere, then energy can be transferred from one filament to another. And as I mentioned earlier, we have some evidence to suggest that even in the nonlinear, in the what we call the linear regime, or if you like, that super filament regime that was talked about earlier today, we have some evidence for the change in that for the transfer of energy in that regime as well. What's shown here is actually supporting some of those measurements, where we have measured, used an inline interferometer to look at the electron density in the filament, so very high resolution, spatial resolution, so we can see spatial resolution within the 100 micron diameter of the filament, and very high temporal resolution, just a few tenths of picoseconds, to measure the electron density for different separations. And you can see the electron density of the separation of these filaments for single beam filaments, for two filaments separated by different distances, for different intensities or different powers in the individual two filaments. And you can see particularly on the right hand side, case where we have two filaments at above the intensity threshold for filament formation. You see that in the blue case, the blue line case here, you can see that the electron density starts off significantly higher than the clamped electron density for a single filament, but quickly dies down within a couple of 100 picoseconds, particularly dies down to lower electron densities. Yes, so that reverts back to our characterization of the half-life of this electron density, even in the case for a if you like, a super thermal filament, or the addition of more than one filament together, and what we would call the survival time of the electron density distribution inside the filament, which can be therefore much longer. Sort of characteristic of the collision time, if you like, the electron collision time that you would expect in from an instantaneous injection of electrons into the air. Few small comments with regard to spatially structured fibers, filaments rather. We've been working at this for quite a while. Of course, our approach here has been to do the best laser engineering we can on the laser system itself, whilst at the same time creating enough pulses of enough energy that can be divided up into many simultaneous pulses sufficient to filament. And we have managed to do that up to energies of, well, close to a joule now in terms of energy, by ensuring that the spatial phase of the pulse that comes out of the compressed laser pulse system is planar. And then with such a planar phase distribution, we can then add to that a fixed phase front distribution to the beam, imprinting in essence on the beam a known phase distribution, which then, as the focusing, in this case the self-focusing mechanism starts to occur, starts to drive the intensity distribution into an ordered distribution. Now, this ordered distribution is dependent, of course, on the phase distribution that we put in front of the laser system. And so we can produce radial distributions. We've also created rectilinear distributions here. Radial distributions can be of either sort of eight beam distributions, or as it's shown on the right-hand side here, 16 beam distributions here. well, we're interested in these distributions for several applications. Our initial work, initially published in this publication in Nature, was on the possibility of being able to use these structures to to modify or focus much longer wavelength radiation, particularly microwave radiation, through such structures. And we've looked at a number of different types of filament structures for microwave focusing. There's also the possibility that you can use this type of structure here, as our colleagues at the University of Maryland in Milchbord's group has been able to in essence use this lower density air column to be able to collimate a visible or near infrared light in much a similar way, or at least in an incoherent way. So more on spatial distribution later on if there are questions. Another capability that we've just introduced into our system after much work in laser engineering has been the capability to take the energy stored in a laser system that would be sufficient for, say, as many as 100 filaments. So that takes us, into the multiple hundreds of millijoules per pulse. In fact, this laser system that we have at UCF can now go up to something like about 800 millijoules, and divide that energy into a sequence of laser pulses, all separated by time durations many times the pulse duration itself, hundreds of times the pulse duration itself. In this particular case here, we show sort of a series of some 30-odd pulses, each separated by 420 picoseconds. What is interesting about this particular image here is it's just not an image, it's a street camera image of the output of the laser system, actually taken some meters downrange from the laser system, and a street camera image of the spatial extent of the beam. So this is actually measuring each filament. Here you see each filament in time, and the width of each filament. And you can see that the spatial scale is very much larger than the overall scale of the Townsend distribution that I talked about earlier. The consequence of this is that we, in essence, have been able to stitch filaments together, either with separations of 420, or even that's 30-odd pulses together, or 16 pulses that are 800 picoseconds or so separated between one another. So now we're really talking about the generation of gigahertz modulated ultra-fast nanosecond bursts of pulses. And these have many applications, which I won't have time to talk too much about today. What I will discuss briefly here is some of our measurements of the characteristics of these filaments. So here is the results of our electron density measurements. Now we use the same electron density method of measuring the electron density, but now we look at the electron density between each one of these pulses. In this case actually separated by the 800 picosecond pulses. And you see that more or less, as I think we would expect, that an individual filament will is intensity clamped. The power is the intensity is clamped, but so is the electron density. And so we see that the electron density that starts off at its clamped density of just under 10 to the 16 electrons per cc, and then exponentially decays down to around half of that. If you like, the down through or almost through the or close to the more stable cutoff density that I referred to earlier, before the next pulse comes along. And the next pulse comes along, and in essence, it's exactly coaxial. We measure the coaxiality to around 10 microns or so, and and then the process begins all over again. And you can see how stable that is from one filament to another. So we in essence have produced an ionized column now that is tens of nanoseconds long at critical density. Varies up and down, of course, but it is now an extended filament. These characteristics produced by this laser system. I won't dwell on this system. This is our MTFL laser system at UCF. It's already produced several PhDs in terms of the laser engineering that goes behind it, including the burst mode operation that I just referred to. Here is a picture of the system, similar system that we've built now on the range at Cape Canaveral. Here it is enclosed in the so-called air-conditioned Connex systems. It is fully mobile system, ostensibly, and at the present time is firing down this 1 kilometer range. Our TISTA facility is very close to the rocket liftoff facilities of NASA, farther north on Merritt Island at Cape Canaveral. Yes, so here the laser design here is almost a duplicate of the architecture of the system at UCF. It's smaller in extent and a little bit more limited in energy at the moment, 500 millijoules or so in energy. But we have also now implemented on this system the same type of burst mode capabilities that we have in the laser on campus. Just a very quick overview of the overall facility that we have at the TISTEF laser facility. TISTEF laser facility is now part of the Center for Directed Energy at UCF, a much larger organization. And now we have several laser systems being implemented at this facility. I might also add that at this facility, we're also implementing a new ultra-fast laser system. This is a long wavelength laser system at 10 microns. It's currently a system that employs high pressure 10 micron CO2 laser amplifiers. This brings me back to working on in a different century on a different planet, since I was involved in much of the development of these TEA high pressure CO2 laser amplifiers many years ago in Canada. Suffice it to say that we are activating a MOPA-based system here. It involves a system which involves an ultra-fast solid-state front-end system that uses basically a mode-locked laser system at one with a 1 picosecond pulse duration, which is then converted to a pulse at the wavelength of 10 microns using optical parametric amplification and different frequency generation, and then a pulse which is then will be injected into a multi-pass configuration of these high-pressure CO2 laser systems that we have acquired from Redstone Arsenal in Alabama. Yes, so we are now tooling up and already started to do some campaigns to look at how these ultra-short light pulses will propagate in normal atmospheres. And for this, we have a whole suite of different instrumentation to characterize that atmosphere. And yes, the atmosphere is pretty complicated. Not only we do basically anemometry, which measures CT squared, the variation of the turbulence as a function of temperature, which can be converted by many models into the variation of refractive index by many models, but weather stations and ceilometer, and then we use these three types of scintillometers that make direct statistical path measurements of the changes in refractive index. The focus of these studies is on the propagation of the effect of turbulence on these propagations. This is a topic that our colleague Mike Heller will be talking about in the next talk. So I'm leave some of the story to him. Suffice it to say here, we already started to make some measurements of the propagation of filaments, both as single filaments and as burst mode filaments, as a function of turbulence, as I mentioned briefly. Yeah, this is the setup here. We have Lyman Blazer and the so-called MUHEL system. That's the laser system that produces this burst mode out there on the range. So far, the first series of experiments were done at 250 meters onto a backstop, and filaments produced in front of the backstop. Here is some of that data. Is with both single pulse at 250 millijoules and 8 pulses in a burst at about the same energy. You can see that in both cases we see supercontinuum, which is evidence in our mind to at least some evidence that the filaments are occurring in both cases. And yes, we have some evidence of here. These are images of those filaments taken at different times. And as I briefly mentioned before, different times implies different levels of turbulence. And in fact, we've made those measurements of the turbulence. Here you see the turbulence can change from around 2 times 10 to the minus 15 down to 5 times 10 to the minus 13. So almost a factor of 20 or so in magnitude. And you see a significant difference in the propagation of 8 pulse burst and in single pulses as well. Lastly, let me mention just some measurements that we have also made in a. I thought I had it. We have also made in terms of being able to examine how filament formation will occur at much higher altitudes. That is, at much lower gas densities. At much lower gas densities, we would expect the nonlinear index of gas to go as pressure, and also in this particular manner, I'm rushing to keep in time here. These measurements were made by propagating through an atmospheric chamber that we have constructed here at UCF, which is in line with our MTFL laser system. This is a 7-meter propagation chamber where we can change not only the atmospheric pressure, but we can also change the atmospheric content and add things like aerosols and the like into this chamber as well. So it's not just used for propagation of ultrafast lasers, but also for things like thermal blooming of CW lasers as well. This is a very quick summary of our measurements made as a function of pressure. If I can, I've been unable to get rid of a subscreen here. But here on the right-hand side, you can see the photographs of the filament. This is the characteristic nitrogen emission from filaments that we observe for basically single energy, single filaments at different pressures. And you can see that we have now been in a regime where we can stay within the nonlinear regime. You see also the spectral characteristics of this emission. So we also see continuing emission in continuing emission from these single filaments. So now I'm having yes. So broad brushstrokes here. The data that we measured so far is much in line with our models, particularly the models that are driven by or in which we've modeled all the physical processes assumed in the nonlinear Schrodinger wave propagation codes that we use to model nearly all our experiments. Characteristics are that the intensity in the individual filaments increases as we lower the pressure. That the that the width of the filament also increases, and we have evidence too that the length of the filament, or the propagation distance, if you like, of the filament also increases. In summary, yes. Yes, as I was mentioning, yes. Yes, here's the analysis of our, not so much analysis, but here are the primary contents of our NLSE code. You'll see that where we inserted the variation of the parameters with pressure, both the Kerr lens effect and also the plasma generation. And as I mentioned earlier, here the changes in the model. So in summary, we've looked at spatially interacting beams, particularly with temporally structured pulses. We've looked at burst mode produced in stitch filaments, and our latest experiments over 250 meters out on the laser range. We're now tooling up to do 1 kilometer range, 1 kilometer range experiments before the end of the year. Thanks to our sponsors. Thanks also to, of course, to participants and the support of all the current workers in the Laser Plasma Laboratory at UCF and the graduates as well. And I thank you for your attention, and I hope that I've remained on time. I'm just hoping to time myself, but that hasn't gone too well. Yes, I'm a little bit over time. Thank you very much, Pavel.
Well, it was very interesting. We're so much behind the schedule, so I guess it wouldn't hurt to ask a few questions.
Just a single one.
Yeah, go ahead.
Martin, I see a picture at different pressures. Could you go back to it? The filament image, nitrogen fluorescence from the side at different pressures and different, yes, this one. I think this is a perfect demonstration that energy which you need to add to keep the filament the same, so this is the same scale, is inversely proportional to the pressure. So this is perfect demonstration. I've never seen that. So
yes, in broad brushstrokes, that is the case. Actually, we have gone to very low pressures, but in the low pressure regime, when we go to very low pressure regimes, we are forced, in essence, to abandon just the simple nonlinear regime. So we have to use focusing regimes that actually take us to the regime where the electron density in the filaments, the stabilizing electron density in the filament is no longer clumped. And up to this point, we have not been able yet to make electron densities in measurements at these low pressures. But I agree with certainly with the connotation that you've made, Olga, that in fact, yes, it's inversely proportional to the energy.
Yeah.
Which is also very good news for doing experiments at larger altitude.
Yeah. So the new chamber is perfect, and thank you very much for the great talk. Very nice, great, very interesting.
Thank you.
Well, any other questions? Well, I guess thank you, Professor Richardson. I will move on to the last talk of the session.
Well, Stefan and Pavel, I'd like to, on behalf of everyone at UCF, to thank you for pulling this all together. It's a very nice meeting.
Yes, well, thanks, Papa. That's thanks to Pavel. I agree. Thank you.
Short and sweet, yes. So.
Great.
All right, so let's welcome Dr. Michael Haley from the Naval Research Laboratory, and he will be talking about the ultra-short pulse propagation in turbulent atmosphere.
Good day, everyone. Can you hear me all right?
Yeah.
We can hear you, yes.
Okay, great. And I should be able to see my presentation next.
Yep, we'll see it.
Okay, wonderful. Well, thanks again to the organizing committee for putting all this together. I'm going to close these. So washed out. Okay. So today I'm going to talk about some of the work we've been doing over the last several years on looking at nonlinear self-channeling in turbulence. This is work that's been done at the Plasma Physics Division at NRL with collaborations with AFRL and NSWC Carderock. So obviously this work couldn't have been done without numerous collaborators, both internally at NRL, as well as the Air Force Research Lab and NSWC Carderock. This work has been supported by the NRL base program, funding from ONR, and as well as the, I guess it's now JDTO. So basically the idea we first came up with and was first published in 2017 was this idea of nonlinear self-channeling. So the concept here is kind of different than what you think of traditionally when you look at long distance propagation. Typically, when we talk about propagating laser beams long distances, trying to create a small spot, we usually think of a very large aperture telescope that then focuses downrange. Unfortunately, that's can be kind of prohibitive when propagating these very high peak power pulses that undergo nonlinearities, because that large beam samples turbulence. And what turbulence does is it introduces phase fluctuations across the phase front of that beam that see instabilities that cause the beam to break up. And typically this is seen as breaking into many filaments downrange. So the idea that we came up with to try to avoid this was what we call nonlinear self-channeling. The idea here is instead of trying to launch a large diameter beam and go long distances, we launch a relatively small beam. And then we use nonlinear self-focusing to just offset diffraction. So the beam effectively acts kind of like a pencil beam, and it just continues to propagate over many Rayleigh lengths. Now, why this is advantageous for propagating through turbulence is that turbulence is made up of many large scale size of eddies. And typically the smallest eddies, we call the inner scale, is dictated by the viscosity of the liquid. So there ends up being a scale size where there really aren't any eddies smaller than that. And by propagating a beam smaller than those smallest eddies, the beam will still undergo deflection, which basically is viewed as wander of the beam, but it won't sample any intensity flux or phase fluctuations across its whole phase front that would ordinarily cause beam breakup. So this is the concept that we have here. So we start with something a normal short pulse system, and then we launch a relatively small beam and let it propagate over long range. So this started off as a purely theoretical and numerical work published back in 2017. And then we began to do a large number of experimental campaigns to validate that. Well, so one of the first things that we wanted to do is, we kind of were hoping to do a real science experiment. And so to do that, we needed to find a way in order to introduce controllable turbulence, which is a very difficult thing to imagine, especially when you're thinking about long distances. We're talking about kilometer ranges, which usually means going outside, and nature kind of doesn't often corroborate with us. So we came up with this idea of creating this turbulence generator based off of heater wires. Why we did this is because due to the high peak powers we're dealing with, things like ordinary phase plates that are made of plastics ideally wouldn't really work. One, they don't produce distributed turbulence, and two, due to the high nonlinearity of the material, they can introduce nonlinear self-focusing, which kind of defeats the purpose. So this concept is based off of just standard heating wires that many people would use for instance, melting snow off their roof. So what we do is we take a number of those heating wires, and then we string them over a long distance, and keeping them tight under tension and suspended over little stands. And by doing this, we can generate natural Kolmogorov-like spectrum turbulence. The example of the power spectrum of acceleration for the turbulence is shown on the bottom right here. And it indeed exhibits both an inner scale and an outer scale, much like natural in turbulence. Also, by controlling the voltage on these heater wires, we can control the strength of turbulence. So we are able to show that we are able to control the strength of turbulence over 5 orders of magnitude. So ultimately, it's proved to be a really unique device for generating turbulence in a controlled environment. So having that design in place, we started doing experiments. So back in around 2015, 2016, we started doing relatively short-range laboratory-based experiments at our laser lab at NRL. These were within our lab. We could generate over a single pass of about 30 meters And then by triple passing, we can get up to about 90 meters. And this is using a pretty standard TIE Sapphire laser, the 5 millijoule, 35 femtosecond, 1 kilohertz TIE SAF system. From there, we moved on at AFRL at Kirtland, New Mexico. They have the 40 terawatt laser system, though we did not use any of that. We used only about 5 millijoules there as well. But they have a very long corridor that provided us up to 180 meters, single pass, or up to 540 meters, triple pass. And then finally, and by going to that longer range, we could start looking at deep turbulence, because the turbulence generator, while it could generate quite high turbulence, we needed a longer path to really generate deep turbulence, where you get very large phase fluctuations. Typically, we kind of say with Rytoffs around 1, you're seeing phase changes on the order of 2 pi. So finally, our most recent campaigns were at the David Taylor Model Basin in Carter Rock, Maryland. So this is an indoor facility. It's 1 kilometer long, and we are able to propagate up to 900 meters. And so we actually went and installed our turbulence generator over the whole distance of this indoor facility and looked at this nonlinear self-channeling as a function of turbulence. Okay, so a little bit more about Carter Rock. As I mentioned, we had 850 meters of continuous indoor turbulence generation. So here's an example of just 1/2 of the range. So this is actually a model basin. They test and design hull designs in here. So there are actually 2 large water basins. And then there's a gangway in the center, which is where we set up our experiment here. So here's a better example looking down range. So you can see here our turbulence generator that's set up in the center aisle, and then we propagated our beam downrange. And you can kind of see this general schematic here, where we had our short pulse laser. We actually we stretched it out to allow for GVD compression, and then we propagated downrange. And at the end of the range, we had cameras to monitor the beam profile, and then we also had a second order frog to measure the temporal dynamics of the pulse at range. The turbulence generator itself, we could generate turbulence from 10 to the -3, which is really quite low turbulence, and then all the way up to 10, which is very high. The neat thing we can do as well is, due to power constraints, we had to break the turbulence generator up into 12 individual zones that we control remotely. So we could create inhomogeneities in the distribution of the turbulence. For instance, like Martin mentioned, we could look at paths in which we would be going up in the upper atmosphere and looking at where turbulence tends to fall off as you move away from ground level. This is quite a installation for us. It took about 2 weeks to build and required about 8 kilometers of heater wire. But when all is done, after building it, we can usually get the system up and running over the course of a few days. So we did a large number of measurements looking at various beam geometries, beam sizes, focusing parameters, etc. So what enabled this is we use a coherent Estrella. This is a commercial system, a standard TIE SAF system, 800 nanometers, 1 kilohertz, up to 7 millijoules, 35 femtoseconds, and we were able to stretch the pulse out all the way out to plus or minus 3 picoseconds, depending on the sign of the group velocity dispersion term of the chirp. Has very good beam quality, which is critical for long distance propagation. You don't want the beam breaking up just due to bad beam quality. And then we also installed a dazzler, which is an electro-optic device that allows us to change the higher order dispersion. And I'll get into those results later. So why is it important to worry about atmospheric dispersion? Well, as many of us probably know, in atmosphere and all materials, there's dispersion. And so what that does is it changes the phase velocity of the group velocity of the various colors of the laser pulse, causing the pulse to naturally either compress or stretch depending on the predefined GVD that you've applied to it. So air is naturally positively dispersive and to GVD. So we would apply a negatively chirped pulse to allow the pulse to compress at range. And why this is important is because the condition for us to maintain nonlinear self-channeling is that we need to have the beam just at 1 P over P crit. But air, like all materials, has absorption, scattering, and diffractive losses. So our beam is naturally losing energy as it propagates. So to combat that and maintain that high peak power, we have to compress the pulse. And we do that using chirp compression over this long range. So one of the first things that we did in the experiment is to verify that the amount of compression that we needed was indeed what is predicted. So air, based on our system, based off the duration and the spectral components of our system, we would expect that our system, when stretched initially at 2.5 picosecond, would compress down to 1 picosecond over this 900-meter range. So we set up our frog. And so here's just a general schematic of how a second-order frog works. It's the type of spectrally resolved autocorrelator, effectively. And we went and we measured the compression of the pulse downrange. So you can see down here some raw images of what the frog gives us. So this is a frog image, it's a spectrogram, so it gives you time and wavelength information. So we initially launched this relatively long multi-picosecond pulse, and then we measured it downrange, and we see that indeed the pulse is compressed. And so and what was interesting, we saw two kind of conditions. One where we get purely linear compression, where you start with a relatively Gaussian temporal profile, and the pulse then compresses down and shortens, still maintaining its Gaussian-like property. However, since we are propagating in a very nonlinear regime, we can start introducing not just transverse nonlinearities, which is what we're using to Kerr self-focusing, but we also introduce temporal nonlinearities, which drive things like self-phase modulation, which usually starts to show up as pulse splitting. So we see some images where you get this kind of four-leaf clover-like image, and when you go and you extract the temporal profile, you see that indeed the pulse is starting to split temporally. So that's an indication that we were indeed propagating in this very unique nonlinear way. Unfortunately, we would have liked to have done a really thorough statistical analysis of this to see if there's any effects of turbulence on those temporal dynamics. Unfortunately, due to beam wander at these long distances, it's very difficult to capture enough of the beam in the limited aperture of the frog. Okay, so here's some examples of some of the images and videos that we took downrange. So what you'll see here in the top row are true color images of the beam. So we have a diagnostic that measures both the strength of turbulence as well as the inner scale that we call the LIST diagnostic. And it's based off of beam wander and intensity fluctuations of a Heaney. So this is what you see in the red is just our diagnostic Heaney, and then the saturated region right here is the USPL. Now it's saturated on our true color image, but you'll see we have a nice 12-bit kilohertz camera that's recording the actual beam profile of the USPL down below. So I'll start these videos, and what you'll see is that the true color one, let's see if we can get going too. Okay, get both of them going at the same time. What you'll see is that at very low turbulence, you can see a little bit of the phase front distortion due to the turbulence and the rising heat from the turbulence generator in the Heaney. But what we're seeing is that the USPL maintains a very nice tight spot on the order of a centimeter, and then kind of wandering around. And as we turn up the turbulence, we see that, let me turn these ones off. We see that the turbulence is causing the Heaney to expand well beyond the constraints of our backing board, and see these very large fluctuations in intensity due to scintillation of the beam. However, when you look more detailed at the USPL pulse, you see it's still maintaining this very small size. The wanders went up significantly, which is one thing we'd expect. However, it's still able to maintain this nice small spot. So this is what the raw data looks like. So that's a matter of now taking that and going and doing a full data analysis on all this camera work. Okay, so one of the first things I mentioned is that we expect the beam wander to maintain and wander the same way as it would linearly, because the USPL, while it is smaller than the inner scale, is still sampling all the eddies. So it's actually slightly refracting off of those. So it's going to wander in the same way you would expect a traditional linear beam. So this plot here shows that. So the solid line is linear theory for turbulence-induced wander. The green circles are what we got in experiments, and then the diamonds are from our HELCAP code, which is a high energy laser propagation code that we have developed at NRL. It handles both nonlinear and linear propagation, as well as turbulence. So you can see overall they follow the same trend, and actually experiments agree very well with theory. Okay, so we've done that. So now we're looking at the actual beam profile itself. What we found is initially that the whole beam radius is indeed smaller than that of vacuum, but it doesn't quite maintain its initial spot size. So you can see in the plot in the top left, we've got a black line indicating what the expected beam size, or this is a turbulence-induced beam spreading as a function of turbulence. So that's the black line. And then the plots below, those are violin plots that show the probability density of the short pulse beam. So the green is the experiments. Once again, simulations are in blue. And then the black line inside of each distribution plot is the mean, and the dashed lines are the standard deviations. So you can see as a whole, the experiments show that the beam is able to maintain approximately its same mean spot size, but then the distribution increases significantly due to the turbulence. Well, so one of the things that we did then, that's just looking at the whole beam, we did a hotspot analysis to see how that compared. And the reason for that is that while the beam is undergoing nonlinear self-focusing, the beam's temporal profile is Gaussian. So the front and the back of the pulse, where the instantaneous power is much lower, they are not undergoing the same amount of self-focusing as the center of that temporal profile. So effectively what happens is that the wings temporally of the pulse are undergoing different levels of self-focusing. So anywhere from purely linear defocusing to moderate amounts of self-focusing. So that energy is bleeding out, and it tends to weigh the d4 signal measurement of the spot size. So by doing a hotspot analysis, it helps get and remove some of that energy that's on the wings temporally on the wings of the pulse. So you can see on the right, here's our hotspot analysis, and we see that the beam is able to maintain that most intense radius extremely well, even to very deep turbulence. So another thing that we looked at is part of one of the metrics that we used in the initial theoretical work was looking at the amount of power that you could self-channel in turbulence. So once again, these are plots showing linear theory, and then what we see in experiments, and we see that indeed you're able to channel more power than you could ever do in purely linear propagation, typically on the order of about 35 to 40% when you're dealing with very low turbulence. And then as the turbulence increases, that decreases onto the order of about 10%. This is actually very consistent with our previous theoretical work. So this was a really nice check on that work. But the question was, at this point, have we reached that limit? Is there any ability for us to propagate more power? Because we mentioned there that these issues with the front and the back of the pulse. Can we do some smart tailoring of the pulse to try to increase the amount of power just channeled? So that's where our most recent work was. Is we actually acquired this is a dazzler from Fastlight. So this is an acousto-optical programmable dispersion filter that allows us to arbitrarily apply higher order phase and amplitude to the pulse, so up to fifth order dispersion. And it's synchronized all the way up to 5 kilohertz. So we can every single pulse is going to be have these higher order phase tailoring to them. And so we did scans of GBD and TOD over a very large range, and we actually observed that indeed by having higher order dispersion control beyond the traditional GBD, that we were actually able to produce an even smaller beam, about a factor of 30 in whole beam and a factor of 60% in self-focus spots. So an example here of the lineouts that we produced is down below. So this is a plot of third order dispersion and as a function of beam radius, still plotted in these kind of violin-like plots. And you can see that the ghosted out region here is without the dazzler in the system at all. So we're not doing any higher order dispersion compensation. And you can see that the beam spot size is much larger. But then by controlling the third order dispersion, we're able to create an even smaller beam with even a smaller statistical spread at range. Okay, so that's basically where we are to date. We've had various experimental campaigns looking and examining the physics of self-channeling. And they provided actually very excellent benchmarks for our simulations. We started out doing just showing that we were able to self-channel over many Rayleigh lengths. We moved into looking at the effects of deep turbulence, then eventually looking at the effects of temporal spreading due to GVD, and then most recently looking at the effects of higher order chirp correction. And really our ongoing effort that we're working on now is really looking at how we can further push those limits on self-channeling. For instance, doing more advanced pulse shaping, if ideally something looking a lot like a top hat may be really effective, as well as looking at other wavelength ranges. And with that, that's what I have. So here's a number of references for any interested parties. And I thank everyone for their time and attention.
Well, thank you very much. Very interesting. Are there any questions from the audience?
Thanks a lot. Yes. Can I ask how? Can I ask you? Very nice talks, by the way. Thanks a lot. Thanks a lot, Michael. May I ask you how important? Could you give me again a feeling how important is the third order dispersion?
So it actually, go ahead.
As compared with a regular second order chirp.
So for short distances, the second order is the primary one. What we found is you go to longer distances, it has to do with the laser design. That traditionally you're just using the separation of the pulse compressor gratings, so to control the GVD. But the way those Tracy-like compressors are designed is that when you when you detune them, you're actually introducing higher order dispersion, particularly in third order. And so the sign actually with those compressor gratings flips. It goes from positive to negative and then back again. Whereas in air, GVD is positive and TOD is positive. So what you end up doing is you're adding more and more the wrong sign to your third order dispersion. So eventually, as you go far enough, especially if you have a very broadband source, the third order dispersion can become extremely important. And we think we most recently just did a campaign this last fall, which I haven't been able to present yet, at 1.6 kilometers.
1.6, right? So 1.6 kilometer is okay for third order dispersion. So you can.
So we went even further there, and we found that we started to hit limits on the compressibility of the pulse because we were going so far.
Thanks a lot. Great.
No, my pleasure, Olga.
Well,
can I ask a question, sir?
Sure.
Thank you for your talk. What type of loss mechanisms one can expect from turbulence?
So turbulence itself isn't really typically provide much loss, other than what it can do is it can effectively it can introduce in one way a higher order mode structure. And so those higher order modes tend to diffract faster in one way. But turbulence itself is not really introducing any traditional loss. It's more the atmosphere itself, water vapor, aerosols, things like that lead to absorption scattering.
So do you plan to consider propagation of Bessel beams or Hermite-Laguerre beams in the atmosphere? Because they are, I think, robust for diffraction.
Yes, I think we're very interested in that, getting a good workup on how that changes the beam quality. There's been obviously some great work that's been done looking at how those types of beams can outperform a traditional Gaussian beam, especially in turbulence. But it's very interesting, especially the ones that are, cylindrically symmetric. When you introduce them into an environment that has no symmetry, how they start to distort the beam is kind of a very interesting subject area.
Mm-hmm. Thank you.
May I ask a quick question?
I'm the last talk, so I don't see any reason why not.
So the question is, how are you going to make Bessel beams if it is 100 millijoule or more in the pulse?
Oh, that's a good question. I've seen some all reflective phase devices now.
Mm-hmm.
We've done that, but yeah, that becomes very non-trivial.
Absolutely. Okay. Thanks for your answer.
Okay. I guess if there are no more questions, we probably should close this meeting. Thanks for all the speakers for accepting the invitation on very short notice. I hope this meeting returns to its usual in-person format. Sooner than later, we can all meet in person. Well, thanks, and well, have a good day.
Thank you very much, Pavel. Thank you, organizers.
Yep.
Thank you so much, Pavel and Stefan. You collected us together and did a great job, and we all are very grateful to you. So
Okay.
thank you so much. Thanks,
That's
Pavel.
awesome. Thanks.
Stefan,
Yep.
are you here? No, he's not here. Okay, thanks to you.
Mhm.
Thanks, Pavel.
Yep.